Now, machine learning potentials. This talk will be about representing potential energy systems. I need to do that, I will tell you in a second. We are not a typical machine learning group, we are actually a quantum chemistry. We always turn to machine learning when we don't know how to continue with quantum chemistry. And so machine learning potentials is one of the fields that we have been working on. And let me first explain to you why we were forced to look into this. I guess most of you are familiar with how successful machine learning potentials have been, especially in material science. And so we thought that we can exploit that also in chemistry, reaction chemistry. So this is some of the background. I kind of have 4 slides on the background to explain to you what we actually need in what we want to do. And so we want to do chemistry, and we want to predict reaction chemistry, and on a broad scale, so big data. Right? The way we do that is with automated network exploration. So we exploit quantum chemistry tools to figure out reaction networks of basically any system. Catalytic systems. We want, of course, we want to do design, we want to understand chemical processes, and we don't want to be restricted in any way, not with respect to chemical elements, not with respect to size. Okay? And what we actually do is for our reaction networks, you see compounds connected by reactions, but you need to be aware of that when you do quantum chemistry, each compound is represented by different conformers, that's indicated here. And then what actually reacts are conformers, right? And we have a set of elementary steps. Rather than having one chemical reaction that you discuss in chemistry, we would have a set of elementary steps that connects any two conformers of a given set of compounds. Okay, and we want to elucidate these networks automatically, because there's no way that you can do that by hand. And that comes with certain constraints. We do that with software that we have developed in the last 6 years or so. You see how big the project is. We call it the Science Software Project. It's open source, free of charge. It has various modules. These modules are standalone modules and they also work together. Point is that we have a module that is called Chemoton that does the exploration. We do have a graphical user interface that's called Heron. Everything communicates with the database where we store all the transition states, all the stable intermediates, and so on, and we can dock this to various programs that do raw data generation. Now here you see an example for brute force exploration with this software of a reactor system that's just very simple, propylene oxygen, so super simple. And this graphic here shows the explosion of structures that you see. So we do an exploration with an approximate DFT method. It must be fast. DFT type binding, like this DFT is super expensive. We restrict ourselves to barriers that are smaller than 200 kilojoules per mole. We don't see conformers. We can switch this on, but we can switch off, so no conformers. We limit ourselves to this size of molecules. And then we find a reaction network of 4,200 compounds, 6,300 reactions. In order to get that cost us 1 billion energy calculations and 5,000 days of simulation for this simple system. And so my message kind of is, no matter what chemical system you study, it will be a nightmare on the network. And that implies that we can't afford expensive methods, electronic structure methods. So this is why this was done with type binding DFT. Actually, that was done with DFT. Now, I never know how the DXDP is. I get a network. I assume that the energies are not that good. That's fine, I can improve the energies. But I can only do that if I can trust the structures. Can I trust the structures? Depends. And for organic chemistry, we have seen failures, which are dramatic. For transition metal chemistry, we would expect regular failures. So the problem is we have a fast method, we get a network, but we don't know what it tells us. Because we have no clue with the accuracy. And so we need to come up with something else rather than type binding DFT. We need something that is fast as force fields. But it needs to be as good as electronic structure theory. And given the title, of course, we think about machine learning potentials. But machine learning potentials require training, right? And we can't afford the training. Why can't we afford the training? Well, I want to look at reaction chemistry on a regular basis, where if I come up with a new reactant or a new system which I want to try, I don't want to spend weeks on training this until I can do an exploration or a big question. And that's not possible with the typically available machine learning potential. You might argue that there are now a couple of generous models available, right? And which is true. And they most likely work in material science well, where I'm not an expert. They don't work well in reaction chemistry. Reaction chemistry means that we need representation of the potential energy surface along the paths. Okay, so they need to work well across the whole surface, not help you identify the proper minimum. So you require more. So let's look into machine learning potentials. So this is a starting point. We have this is our electronic energy. We decompose it in this way, right? So the idea is that the total energy is the sum of atomic contributions. And there's this classic paper by Biela and Michele Parinello from 2007, which kind of made this idea work. Right? Then see, now I'm looking at these atomic contributions on the next slide. So you see here the expression of a machine learning potential for the atomic contributions. I mean, you're used to these neural network representations here, but of course it translates into an explicit analytic representation of our energy contribution, which is nice. It comes with many parameters that a neural network potential incorporates, and they need to be fit somehow. A key ingredient that encodes the structures are these G here. The G's are the structure descriptors, and we use, in our case here, atom-centered symmetry functions. They are kind of explained here. Right? So for each and every atom in our molecule, we need to represent the atomic environment. And that is done by these G functions, where we have radial contributions and angular contributions. Now here you see first the analytic form of the radial contributions. You see an exponential here, you have a cutoff function. We look at, we add the oxygen atom, and we try to figure out what is in the vicinity of the oxygen atom, but we don't want to reach too far out, because otherwise that wouldn't scale properly. Right? Now, these are functions defined by Biela in 2011. The problem is, if we want to use them, we get too many of these entries, and we have to replace them by something else. This is why we came up with what we call element-embracing atom-centered symmetry functions. And the idea is that rather than having radial functions which are arranged like this, we have just one vector which depends on, well, basically information that we take from the periodic table. Right? So we have kind of descriptor information that relates to where our elements are in the periodic table. And this limits the number of entries in this G vector. And we also have angular functions, and we transfer this idea also to the angular functions. Now, so we take this original idea by Biela for the machine learning potential and these atom-centered symmetry functions. We modify the atom-centered symmetry functions, and we now can represent the neighborhood of an atom in a very efficient way, independent of the number of elements in the system. Now the next point is that we need to make these machine learning potentials flexible. Right? Because when you think about, so flexibility will be the next issue. Because when you think about this idea of exploring reaction mechanisms and doing even design, because if you need that new species are coming in, so the potential energy surface is constantly changing, we are faced with the fact that we have an influx of data that's changing constantly. And we cannot stop at every instant in time and retrain the whole thing. That won't be efficient. The problem is that, of course, electronic structure theory, that the applicability is broad, because we deal with electrons and nuclei, you don't see the elements, but it's expensive. For force fields, you can be efficient as well, but you need to have, you need to train and reparameterize and so on. The question is, how flexible can be machine learning potential for this specific application? And so let's look into training of the machine learning potentials. So this is what you would typically do. Right? Say you have certain data which represent the reactivity of some system. You train the machine learning potential, and then you can work the machine learning potential with that system. Now, when you extend the chemical reach, so you extend into chemical reaction space, you get more data, you would retrain your machine learning potential, and then you would work with that. And then you see even more data and you retrain again. So that is not the way to go. Instead, we propose something that is along the lines of lifelong machine learning. Okay, so the idea is that we initially have some data, and this is actually the situation that we face in the exploration of reaction mechanisms. So initially we have some data, and we can parameterize the machine learning potential on that data, and then we will see new data. We don't want to forget the old data, and we don't want to start training right from the start, because that would be super inefficient. And then we will continuously see more data, and we don't want to forget the old data. And we need to come up with a scheme, an optimization scheme that can deal with that. Basically, that implies that you need to have a scheme for adaptive data selection. So, there are basically, this is a very important slide, I'm sorry. There are basically two ideas behind this. So data that is redundant should be so data that is redundant and it's seldom trained, that you don't want to have. You want to get rid of it. Data that is kind of inconsistent, is likely to be inconsistent if it's very often trained, but it's still badly regulated. So you need to deal with two different kinds of data, the redundant data and the inconsistent data. We have basically, as the data that's incoming is information about structures. And for each of the structures, say I, we will have a training probability. Initially, that will be initialized to be equal for all the structures that you see, and then in the process it will change. And we have a basic scheme that allows us to change these training probability on the fly. And through this scheme, we can focus on the data that is actually needed and forget the data that is redundant. How do we do the optimization? Well, there are various optimizers available. This is one of them, adaptive moment estimation, ADAM. That's a paper, has been cited, I don't know, more than 140,000 times. So this is a very well-known optimizer. To fix the parameters, it depends on information from the loss gradient and the squared loss gradient in this iterative fashion. And there's a specific way to calculate the step size update, which then changes the values. Okay? So ADAM is one option. Here's another one, the resilient backpropagation, R problem. Relies on the loss gradient, has a different way to set up the step size. Right? It realizes different ideas. For instance, it can change the step size if the gradient sign doesn't change. If it changes, it basically means that you have crossed the minimum, and then you would actually have small step sizes, so in this way it's adaptive. Now, let's see what we get with these optimizers when we look at an example from exploration. This is a classical example, of course. It's an SN2 reaction. This is a generic reaction. Here you see the different components, and we created reference data for this reaction. 90% of the data was the training data, the rest 10% was the test data. The chemical system eventually was in 42 SN2 reactions with 10 different chemical elements, and we looked at 8,600 conformers along the reaction, configurations along the reaction coordinates. The data that the reference data we could use with PDE, but we could use any other electronic structure method, of course. And now we need to optimize the machine learning potential. And here you see the results for ADAM and RPROP. So when you look at RPROP, convergence is fast and smooth, but you get somehow stuck in a local window. So the error here measured for the energy and on the right hand side for the forces does not go, at some point it gets stuck, it does not go further down. ADAM is much better, but super noisy. So both of them don't work. And this is actually what we figured out when we were trying to optimize our representation of the machine learning potential. So fast and smooth convergence was possible with this RPROC, but not with Adam. High final accuracy, we get with Adam, but not with RPROC. And so we had to play around with a new optimizer that can deal with the situation, and that basically unifies ideas from RPROC and Adam. We call it the core optimizer, stands for continual resilient optimization. So we combine ideas from Adam and RPROC. I don't know whether I should walk you through this, because you should have paid very careful attention to the notation that was there before. I invite you to read the paper, of course. So what the take-home message is, we combine ideas from both, and we also introduce new ideas where we change this gradient step here in the Adam optimizer by changing the speeder parameter and so on. Okay. Have a look at the paper which introduces the optimizers for all the details. And it's technically a bit boring to read this. It's as it is. Let me show you the results. So this is the same situation, same data. You see again the Adam and the RPROC data from before, and now with this core optimizer, we basically achieve what we wanted to have. We quickly converge to the result we wanted. We don't get stuck as in RPROC, and we see a bit of noise, but we don't see as much as in Adam. So this core optimizer works very well for the lighter machine learning potentials nowadays. Here you see a comparison for the same data of different optimizers. So this is our score. You see Adam, you see RPROC, and there are also other optimizers. These other optimizers were not as good as Adam and RPROC. This is why I didn't show you. Okay, so we were only forced to come up with a new solution because none of the solutions actually work for us for this specific case that I introduced you to. And of course, when we submitted the paper, reviewers said, okay, but how does your optimizer that work for other machine learning tasks? And here you see standard machine learning task that we then later on tested. This is a paper that's on the archive. It has been submitted for publication, but the review process takes for ages. So we waited 4 months to get reports. Never mind. So the point is that even if you forget about the machine learning potentials and you go to general machine learning tasks, the core optimizer actually performs pretty good. Okay, seems to be of general applicability. Now let's look into data. So when you compare the data that is needed for the training, you see that the number of training data is reduced by core, but the accuracy is, of course, is still as good as Adam, if not better. I have to put these figures here. Yeah, when you compare this to these slides. The RPROC curve stopped here because RPROC reached convergence also to the core solution, or to a solution that was not good enough. Okay, now we play around with the data that we have to figure out how the lifelong learning actually works. So we had different fraction of data that was included into the training, and then the first training, and then later we added the remaining data. And basically what this figure should show you is that the error obtained is pretty low, and the lifelong learning works very well actually. Maybe here's a better figure. So if you start from the start with all data, you would get this curve. That would be the best solution, but we don't have all data from the start, and we don't want to start all over again. Right? Now, lifelong learning gives you this curve. You have some data initially, and then we get more data, and you see we can sneak this in smoothly and then also obtain the final result. So apparently this idea is working for rolling data coming in. We can do that also with a twist on the chemical perspective, where we have some data that refers to specific structures in our reaction data, and then we include other data subsequently, and that also works. And another feature picture that we have, which is very important for us, we need to understand, because I told you that the type binding DFT never tells you how good the data actually is. We need to have uncertainty quantification. This is something not predictive that has been in the focus of our work for many years actually, and we don't want to give it up when we switch to machine learning potentials. The uncertainty quantification, when we go to neural network potentials, is of course done by ensemble averaging. Right? So we create more than one machine learning potential, and then we see how they perform, and from the results from the scatter that we get, we draw conclusions about the uncertainty. And that also tells us where we will need more data for improving the machine learning potentials. This is basically all I wanted to tell you. The conclusions are that this concept of lifelong machine learning potentials actually unites accuracy, efficiency, and flexibility. For that, we introduced a more universal descriptor that was based on these ACSFs by Biosciences, and we call them element-embracing ACSFs. The machine learning potential was a neural network potential, and certainly quantification we do by analyzing the ensemble. And for the optimization, we had to come up with a new optimizer, which we call the co-optimizer. What we are currently doing is that was the toy problem. We are now trying to establish the lifelong machine learning potentials in real-life mechanisms of storage. That's what I'm doing. That's all I wanted to tell you. All the work on the lifelong machine learning potential was done by Marco Eckhoff. This is Marco, and the funding for that came from ETH Zurich. Therefore, thank you very much for your time.
A question, yes, here it comes.
Thanks for the great talk. On slide 23, you were mentioning, you were talking about the lifelong learning data selection methods, and you had these composed functions, these these F sub S and so on. Could you go into a little more detail how what this composition of F functions means and how you calculate this training probability?
This is already going to lose
Okay. All right. Okay. Thank you nonetheless.
Anyone else?
A question slightly related. So with each training, in each adaptive sampling step, you pick a fixed number of training data points. You subsample a fixed number of training data points according to this scheme. So where does this number come from? And would it, obviously, the point of lifelong learning is to forget, right? But at some point, if you realize that you just don't have enough data points, that number surely should grow, right?
First of all, this selection of data points is just for the artificial example. The real-life example is to have some data, and if you do more data, to create the data that we create will be some in this case, DFT data for our configuration. And then you would explore based on machine learning. We have uncertainty quantification, so we kind of understand when the model is created, and this is very automatically what we do.
But I think what I really like here is the aspect of forgetting is quite important, because very often in active and adaptive learning, the initial distribution of data is not very good. And once you get to training more data, it can be quite good to get rid of some of these original data points, because they are very unequally distributed.
And this scheme,
yeah.
This scheme doesn't.
Thank you. Thanks. So, thank you for your talk as well. From an implementation point of view, did you implement those already, like using TorchAny or PyTorch, for instance, including like the adaptive sampling stuff and the core optimizer? Are those done in TorchAny? Okay, so And is the code already available, or?
I think we did.
Okay,
So everything we do will be released. Everything is open source. Everything.
great.
And I must admit, when we have students projects, I'm not on top of that there has to be. Actually, we are forced to release from this by rule of the API page. So it should be easy.
Okay,
There is a review of the code that is done by a search person. And I have just one search person that does all the code review.
I feel your pain. I feel your pain. Okay, thank you.
I think for the benefit of the speaker, we make this the last question, okay? There we go.
Thank you, Markus. Very nice talk, and very nice idea to select data. And I would like to ask, how do you make sure that you don't overpopulate specific regions of the conformational space? So in other words, how can you control that you don't add data that they are already there?
And again, first it is key. Data that is redundant. So you kind of understand what is the redundant data and then you also way it is
I will read that paper very carefully. Thank you.
I think we thank the speaker final time, and then we'll let the word to Roland.